In this video, I'll be talking about implementation of implicit solution for advection diffusion. In the last video, I showed you how to do that using explicit discretization of advection equation, and this time I'm going to show you the implicit version of it. Implicit in time, I mean. So if you remember from advection equation, we had derivative of u with respect to time plus v times derivative of u with respect to x equals 0. We moved v du dx to the right side. We used a backward Euler in time, so that's why we have n minus 1 here. And on the right side, everything has to be at time n because that's backward in time. And it's going to be implicit because every variable at time n is unknown. So I have unknowns on the right, I have unknown on the left, so totally this is an implicit method. On the x index, on the left side I use discretization upon xi. On the right side I have to do du dx, so I'm going to use backward Euler as well, assuming v is positive. That means velocity is from left to right, so the information is going to propagate from left to right. I have to use the x points, or the points behind point I. So that means I have to do I minus 1. Alright, so we turn this into a matrix, if you remember. And then, so this is the matrix we got. We apply the boundary conditions by multiplying the first column times the known boundary condition at x equals 0, or the left boundary condition, and then we move this column to the right side. If you follow this red arrow here, that is coming from the boundary condition. So at the end of the day, I got a matrix with n minus 1 times m minus 1 if you think of m variables, because the first one is known, the boundary condition. Totally I have m minus 1 unknown in my list. So this is at every time point. At every time point you have to solve this system to get the values at every x. For the next time point you have to update this matrix and then find the new values by using the values we calculated from the previous time points as the right hand side of this equation. So let me switch back to the MATLAB script and show you how we can implement implicit version of advection equation. So there you go. We clear the screen as before. We have 200 discretized points along the x, 100 points along the time axis. Initial time is 0, final time is 4. Minimum, or the lower bound on x, is minus 10, upper bound is plus 10, velocity is minus 5, the velocity is negative for now, which means the flow is from right to left. Skip, this is a variable that I use for movie making. I'm skipping every 4 frames, and basically I pick 1 out of 5 to just create a movie, because I don't want to have a lot of frames. Makes my movie a bit bigger than I can handle, or a lot bigger than I can handle. Alright, so we're going to discretize our time vector from t initial to t final with nt discretized points. dt, or the time interval, is going to be the difference between 2 successive time points. Same thing to x. I'm going to create x vector from left to right with npt as number of x discretization, and the x is going to be x2 minus x1. I create the mesh grid, and this mesh grid is nothing but what we covered I think last time, if I remember, from page 169. At the bottom of the page I had this cartoon showing that how we are basically discretizing our point along the x in time. So horizontal axis is x and vertical axis is time. Every point corresponds to a specific index n and j. So n in time, if you think of this point in the grid, that is corresponding to tn and xj. So the point on the left side of this is going to be xj minus 1. Any point behind this is going to be time n minus 1. So just to remind you, if the velocity is positive, wind is coming from left to right, which means information is propagated from left to right, or the flow is from left to right. So that to get the information at this point, I have to use these two. I cannot use these 2 points because the flow is in this direction. That means the flow hasn't reached these points yet. I cannot use the variables that physically hasn't been reached yet. So similarly, if V is negative, wind is coming from right to left. If you want to calculate the information at this point, you have to use any points behind you. That means, or behind and below you. So this is the time n, you have to use n minus 1, but the index for j should be, or the index for x should be j and j plus 1 instead of j and j minus 1. So the rule of thumb, we always go in the opposite direction of the v. So if v from right to left, we're going to use, if you're sitting here, you have to use j plus 1. If you're sitting here and the velocity is positive, you have to use j minus 1. Alright, so we're going to go back to our matrix and see how we can implement that in MATLAB. So, we have our alpha, which is non-dimensionalized velocity, times dt dx. So again, this is the reciprocal of numerical velocity times the physical velocity. I create initial condition, which is a half sine wave, and I create this half sine wave by just getting the sine function, square it, and then times Heaviside function to just cut that wave or this cosine function above and below plus minus 2, plus minus pi over 2. So this Heaviside function actually cuts the wave out of this range. Alright, so by this time now I have my initial concentration distribution as a half cosine wave. Then I look at alpha. If alpha for now, let's say positive, then I'm going to go back to this plot. So to do that, or to solve the problem when alpha is positive, I have to create this banded matrix. Banded because I have only a diagonal and subdiagonal. Everything else is 0. So the way I assemble this matrix is I create 2 vectors, one with 1 plus alpha, one with minus alpha, and then I put this on the diagonal, I put this on the subdiagonal. And the way we do this in MATLAB is I create this dg vector to be n minus 1, basically just ones along this vector with n minus 1 elements. N minus 1 because my matrix dimension is basically n minus 1. So I also create a subdiagonal vector with n minus 2 because subdiagonal always has 1 element less than the diagonal. So then the way I create this A, I just get I use the command diag in MATLAB, diag of this dg vector, so that creates a diagonal matrix with dg on the diagonal. Then I multiply by 1 plus alpha means that I have a matrix with 1 plus alpha along the diagonals. Then I add another matrix to this, and that matrix is also diagonal, but I'm going to put the subdiagonal with shift 1 across the diagonal. So the way we do this is, imagine this is a matrix, I'm going to put this on the subdiagonal. The way to do this is you call diag function, and then you get a shift of minus 1, which means you have to shift the diagonal 1 toward the lower diagonal or the subdiagonal, and then you put minus alpha along that. And that's what this second piece in this line does. Alright, so I'm going to multiply that subdiagonal by minus alpha. So now I have 1 plus alpha along the diagonal and minus alpha along the subdiagonal. Then we go to B vector. The first element of B is 1. So think of this as a B vector. The first element of it is 1, and I'm going to multiply by alpha. Minus goes away because I have a minus here and minus here, so total I get plus. So my B is going to be alpha times a vector which has only 1 on the first element and 0 everywhere else. So this creates alpha, and then I'm going to multiply it by the first element of U at time t. So let's say at time tn, you're going to multiply the first element of u1 times alpha, and then you put that on the first element of b, and everywhere else is 0, and that's what this line does. This piece actually assembles the second vector we just saw. And then the second piece here is the transpose of u at time tn minus 1. That actually corresponds to this vector, so I have to get the values of the function at tn minus 1, So think of this as a row vector, then I have to transpose it to make a column vector, and that's what this transpose does. So you can transpose the u at the previous time point, so t minus 1, and then you add it to the first piece totally, you get your b, then you do the backslash operator to solve for the u at time tn. So by this time you solve the problem, you need to transpose it back to put into the umat, which has the form of the grid. So remember, for the grid, time goes along the y-axis. So that means at every row of this vector, I have the values for every x point. So because u temp is a column vector, I have to transpose it and then put that as a row vector in umat. Alright, so this is at time t, and then you're going to crank up our t index from 2 to n minus 1, or n, and then calculate every row of that vector, or that matrix. Now, let's go to the case where alpha is negative. When alpha is negative, all you do is so when alpha is negative, then here it has to be, I think if you go to page 169, if alpha is negative corresponding to V negative, then instead of having backward in J, then we have to do forward in J. So if you do the math, you realize that you get a system similar to this, with alpha switched to negative alpha on the diagonal, and then I think plus alpha on the subdiagonal. So let's look at here. Yes, you get 1 minus alpha along the diagonal, and then the opposite of what you got in the subdiagonal. So in the alpha plus case, we got minus alpha on the subdiagonal. Now here we get plus alpha on the subdiagonal. Well, on the superdiagonal, I'm sorry. And they get the superdiagonal, and that's why the shift is 1 as opposed to minus 1. In case of alpha being positive, you get 1 plus alpha on the diagonal. Now, in case of alpha being negative, you get 1 minus alpha along the diagonal. Alright, so, and the changes again is coming because we use forward Euler instead of backward Euler when the alpha changes sign. Alright, so we assemble B same as before. This part doesn't change. So basically you get the exact same thing that you assembled here. There's no change here. You solve U using backslash operator, you transpose it and put it back into the U matrix. So by this time we have our U for every time point and X index. So now all we need to do is just apply it. So there are two ways to plot it, either through 3D version or through an animation. So if you want to apply the 3D, then you have to do the mesh function, and you, for every X mesh and T mesh, you draw the actual U mesh. So that's what we do, and that's the skip comes in, because I don't want to plot every row and every column in that matrix. Otherwise, the picture is going to be really huge, and MATLAB is going to be slow. Now, if you want to look at the animation is you have to go over every time point, and for every time point you plot U as a function of X for that time value, which is a row in that vector, or in that matrix. Then you give it a pause for about 0.04 second, and then you erase this plot and you plot the value of the U in the next time point. So because the interval is really short, the human eye would see this as an animation. So basically this is nothing but plotting a couple of mini frames really fast. So let me run this code and see what happens. So here's the wave. Initially it starts from a half cosine wave. Alpha was negative, so that means the velocity goes from right to left, and you see that looks like this. You have a die, you insert a die, initial distribution of a die, and let's say the nano channel is like this, and then this actually diffuses as the flow goes from right to left. And you see that there's a decay of the peak because the concentration is diffusing in space. So this is the concentration as a function of x, and you see this progression as time goes by. So this was implicit version of advection diffusion equation. Advection equation. There's no diffusion here. So I hope this was helpful, and See you in the next video. Thanks a lot for watching.